Awesome.
Yes.
Perfect. I got you. All right. Let's kick off. So yeah, one quick question before we get rolling. So on the chat, the comment about the problem set difficulty. Absolutely. Remember, this is something I just want to put contextualize. The problem sets, remember, those are the practice ones we get every week. Those are not for marks. They're meant to be something, think of this as a strenuous workout. This is meant to be something for you to work through, try the problems. They're meant to be difficult for you to actually struggle with. They're not meant to be sort of targeted something where it's like, oh yeah, instant recall, got the answer, get into it. They're meant to help you sort of work through that part. So again, if it's something you feel like it's hard in terms of difficulty, that is by intention. Do not freak out, right? This is meant to be something for you to practice your skills and grow off of that. Again, happy if you get stuck in any part of it, come and find us in the Chemistry Resource Center. We're happy to walk through, and also we're going to begin to create video tutorials for working through the problem sets. So you're not just going to have the blank questions and the written answers. We'll actually have work problems sort of developed in the next couple of weeks. Those will be posted in the weeks to come. All right, so we're going to kick off where we left off, discussing the difference between state variables and path variables, right? This is the first law. We've been using this concept of a irreversible or reversible path. We're talking about getting between two states with a bunch of different possible paths, and not all paths are created equal. We do have one overall principle though, right? If we're talking about an ideal gas, and it happens to be a isothermal process. Where does it all start? There's a value which equals 0. As soon as we define isothermal process, what has to be 0 in that thing? Yeah, delta T is 0. That's number 1. If we're talking about an ideal gas, having delta T as 0 is the first one. It also defines, yeah, the internal energy change, delta U, is equal to 0 as well. Why is that? Why can we make those two synonymous? If for a process, the delta T is 0, delta U must also be 0 for ideal gases. Why? What is the reason we can equate those two things? Well, that's a consequence. Work equaling heat, that's a consequence of the first law. Yeah, the reason why for ideal gases, delta T equals 0 means delta U equals 0. There's two ways you can sort of explain it. The best one is, remember, we make an assumption for ideal gases, all of the energy in that ideal gas is directly proportional to its temperature. That's a unit value, that's not a delta. The U of an ideal gas equals either 3/2 nRT or 5/2 nRT. So if we know the temperature, we know how much energy is contained in that gas for simple systems. Which means if delta T is 0, delta U is 0. The total internal energy is not going to change. That's right. So this is our sort of first context. We're giving this a process, and we're talking about these isothermal processes. And last time we left off saying we're going to have a piston. It's going to undergo a change. That change is happening where the overall process is obeying a delta T equals 0, an isothermal process. The path can change. It may not be in equilibrium depending on which path we have. That's a reversible or irreversible process we talked through. Last thing. Now remember, we talked through these pistons and changes. We had to make an assumption about the namings of these things, right? So if I have a process where the piston is getting smaller, or there's a contraction, delta V is smaller, is that an expansion or a compression? That's a compression, right? The delta V goes down, it's a compression, versus if it goes up, that's an expansion. Now, if compression, what happens to pressure? If volume drops, what happens to pressure under these conditions? Volume goes down, yeah, pressure has to go up. And we're talking about whatever the balancing pressure is, and vice versa. They're inversely proportional to each other. So I'm going to sketch out the things that we discussed last time. We had 4 basic graphic systems we talked about, right? And these are our pressure volume gas graphs. So I'm going to put pressure across each of the x-axes, and I'm going to put volume down here. Sorry, pressure on the y-axis, volume is on the x-axis. Now, if I had, in all cases, I'm going to start at the same values, and I'm going to end my sort of second one is over here. Sorry, let me not start and end, but I'm just going to define these two states. The composition we talked about, different paths and different directions can sort of be sketched out into this point. So in the first one, I'm going to talk about a irreversible, if you were going to sketch out in sort of, we're going to call this one A here. In this graph, if we're going to talk about a irreversible compression, no, do I want to do the compression? Yeah, why not? We'll make that one an irreversible compression, okay? So, first of all, if it is a compression, what is happening to volume? Getting bigger or getting smaller? If it's a compression, that means I have to start here. This is my volume 1, and I'm going to get smaller. The volume has to be doing in this sort of direction, right? That's the direction that has to happen if I'm doing a compression. Now, since I'm going to do an irreversible compression, is this a fast change or a slow change? What do you remember last time? Yeah, we're going to try doing it like if we're going to do it by the extreme, we're going to do it as a single step. Everything happens at once. And remember that what we do, if you read off a graph, this is what you change, this is what happens. So if you think about an XY graph, we generally talk about it as the variable we change is up on the Y, and the responding variable, at least that's what we're trying to graph out into this point here. So if I'm going to do a compression, I will do it by first instantaneously changing the pressure. I lift off whatever that value is, so the pressure sort of will jump up. I increase the pressure. This is a compression, which means the volume is then going to shrink as a result of that new part. So this is kind of the step I have. The work we described saying it is a change in volume. It's this delta V, where it's going from V1 to, or V initial to V final. But it's this value, and this would be the work due to compression, and it's the irreversible one. And it will have the area of this, the delta V at this final pressure, this P final kind of value, which is held the entire time that that volume change is happening. So that just gives a sketch of the work that's going involved. For B, we're going to do the opposite direction, still irreversible, right? So I'm going to do, instead of an irreversible compression, I'm going to do an irreversible expansion. That means I'm going to start over here. This is my volume initial. There'll be a smaller value. I'm going to be increasing the volume. So once again, I will do a first step. I'm going to drop the pressure instantaneously. That gives me my new pressure final. We're going to have an expansion against that pressure final, giving me this area under the curve here. This is my work expansion, irreversible. Now these are just one extreme case. There are an infinite number of paths that you could take, infinite number of steps that connect these two parts. If we're going to do the exact same thing now in a slow way, a reversible one, C and D, and let's do them in the same two ways we just did. So I did a compression first. Once again, I'm going to do another compression here, which means I'm going to go from some larger volume to some smaller volume. So my V initials over here, V final will be over there. And I'm going to do it in an infinite number of steps. I want this to be reversible. So the brackets, the change in volume, are still these two parts. The initial and final volumes would be the same as my irreversible case. The difference now is I'm going to do it in a million tiny little steps, and that's going to have this curve. This is what we call our work, the area under this point here. This is our work of compression, reversible. So the difference this time, we're moving from the same two states, we're moving from an initial to final, the exact same as our A case. This, by doing it such that we always maintain equilibrium, that we're always in an equilibrium state, or the system can always be described as by the ideal gas law, then what happens now is, since I take so many small steps, the energy is constantly balanced in that part. The work that we're getting out into this is we always maintain this sort of isothermal case. The path we define here, this line, can actually be given by a simple equation. Now remember, if you're doing this exchange, We're graphing here, remember, this is our ideal gas law, PV equals nRT. What we're actually graphing here, right, is how does pressure and volume behave with each other. And as we've been discussing, pressure is inversely proportional to 1 over volume, right? Where the constant here, if all these things are being held constant in this case, nRT, that's the temperature at which this is being isothermal, N is the number of moles of gas being involved, R is our universal gas constant. This formula actually describes that line. So that line there is a sort of y equals 1 over x kind of formation. The constant here, nRT, depends on the specific one we're doing, but that's what describes this path. This is our reversible path that connects the 2 points at either end based on the number of moles of gas and the temperature that this is happening. The thing is, it doesn't matter which direction we go in this case. The compression looks like this. The expansion will still go from one extreme to the other, the same two volume values. The only difference is the sign is different, right? We're going from the other direction. The path that follows, though, is going to be the same. It will still follow this curve. That's the same formula, which means the work under this one is the same. This is the work due to expansion under reversible conditions. So this is one of the things that we talk about, and then basically one of the ways of describing this. In the irreversible case, the absolute value of work for compression is going to be much larger than the absolute value for the work due to expansion. In the reversible case, work compression equals work expansion. And this is just a result of having all of the energy balanced while this case is happening, while we're actually going through the process on the reversible condition. Again, the mental picture you want to sort of hold on to. If we were to, let's say, do a very rapid change, we take a cylinder, we suddenly squeeze it, we compress it very, very, very quickly. What do you think would happen if I grabbed a cylinder and I just shock compressed it? Would the temperature remain isothermal in that instant after I suddenly loaded it with a ton of energy? No. What would happen to it? If I took a cylinder and I jammed it closed really, really fast, what has to happen to tense? Yeah, heat. In order for this whole thing to balance, it's going to get hot, which means in that first shot, if I were to sort of measure the system right here at this state, it is not in equilibrium. The system is going to get hot. It's not obeying at that instantaneous point the isothermal case. It will return to that over here after heat flow can kind of catch up. Work and heat have to work against each other. We're not breaking the first law of thermodynamics. It's not like this is a system that suddenly we're creating or destroying energy. All we're saying is it is possible to do these transitions where the amount of work you need or the amount of work you get back may not be equal. In that case, if we did irreversible expansion and compression, the energy balance is how much heat is involved in those cases. Versus a reversible system, work is the same in both cases, which means heat must be the same in both cases. Whereas that is not the case in the irreversible one. The heat and work quantities, the values, will not match. The overall delta U for all of these is still 0. If we go from blue to red, no matter which path we take, the overall change in delta U will be 0 because we start and end in an isothermal state. On the path, though, they do not have to behave according to that. We're not in an equilibrium position, so it doesn't have to behave in an isothermal way. And this is something, where have you guys seen this? Rapid compression or rapid expansion, where do we typically use that in the context of heat or heat and work? There's a system, or yeah, engines for sure. There's another one probably that you run into, especially in the summer when it's really hot outside and you want to make it more comfortable. No, not so much. Yeah, air conditioning, not fans. How an air conditioner works, right, is we take a gas, we use electrical energy to do work to compress that gas, and as we do that, as we force it compressed, it releases heat. We then have to have, cooling fans, everything else to move that heat, but it's that process of this rapid compression and rapid expansion we use to sort of to bin heat and move it around in different places. Those are done where individually at the compressor or at the condenser, there's irreversible processes happening. In the end, we're going to be using a lot more energy overall than we're getting back in these sort of cases. It's not a infinite energy system. So instantaneous compression causes a decrease in, compression will be an increase in temperature. If you took a gas and you smashed it, the temperature inside would have to get hot, right? The pressure inside suddenly got very, very big. The volume got very, very big. Temperature would have to balance it out. That's right. Or volume got small, excuse me. So temperature has to balance. Yep, that's right. Okay. So again, let's just go through a couple of questions that sort of talk through these concepts. Now remember, think of these two extremes in your head. What we're really trying to emphasize here is, number one, in an ideal gas system, temperature is our delta U for the overall process. Delta U being the difference in energy between two states. Two, if we've got this difference in energy between two states, there are many different paths to connect those ones. And they're not all the same. They're not all equal. The path variables, how much work and heat gets expended to get between those states, can change. The states themselves do not, the start and stop. So if we were to, first of all, think of an isolated system. Now remember, way back, definitions. An isolated system. What is the delta E for an isolated system? Yeah, it doesn't matter if it's reversible or not. It has to be 0. For an isolated system, remember, what was the definition of an isolated system? What cannot change in an isolated system? Yeah, no loss of energy, no loss in matter. For a system to be perfectly isolated by its definition, it cannot undergo a delta E. There's no loss of energy of it because it cannot escape that sort of system. So one of the things to look for is based on our definition. So again, if this was an ideal gas where the delta T was 0, that makes a very specific case. That means what about the delta U? If delta T for an ideal gas is 0, we know that the delta U or delta E is also 0, right? So these are two conditional ones. The boundary cases we can use to create, to do sort of these kind of assumptions. Next, if a system releases heat to the surroundings and does work, what are the signs of these two values? So let me launch this one. Whoop. What's the difference between U and E? For the context of this course, same thing. Really, if you go back to physics, and again, saying that around my physicist colleagues, they would kill me. E is the value, it's an enthalpic value that we typically use as chemists. It contains a little bit of differences between U, which is the total internal energy of the system. For the concept of this course, they are both representatives of the internal energy, so treat them as interchangeable for right now. All right, 5 more seconds. And okay, and that's time. So the major answer is D. Now remember, look at the wording. If the system releases heat to the surroundings, that means heat is leaving the system. Q must be negative. That's right. If the system does work means it is pushing back, it is expending energy onto the surroundings. Once again, negative. So absolutely, the correct answer here, both Q and W are negative for whatever we've just described. Okay, if Q and W are both negative, heat is what? Leaving or entering the system here? Leaving. What about work? Leaving or entering the system? Okay, What do you know about this process? Does this, the thing we just said, does that describe the isothermal pistons we just talked about? No, why not? Why could this never be a description of the pistons? Yeah, under the context of the pistons, isothermal, we're saying delta E is equal to Q plus W. If delta E is 0, because it's isothermal, Q equals double. Same magnitude, opposite sign. What we're talking about in the isothermal piston case, work is being converted to heat, heat is being converted to work. There's the change off between the two where the magnitude is the same, but the sign must be different. We're balancing the overall delta U of a system. Here, for this one, what would the sign of the delta U or the delta E have to be given that Q and W are both negative? Yeah, it has to be. And remember, the overall first law always applies. Delta E, delta U equals Q plus W. The special case, isothermal, Q equals double W, okay? Good. Next, internal energy of an ideal gas depends only on its temperature. So given that, whoops, let me move this. Which statement is true for an isothermal expansion of an ideal gas? Would an exothermic reaction happen in a balloon? Exothermic reaction in a balloon causing expansion. Yeah, that would be true. Again, as long as there was based on the last question, if we had an exothermic reaction, we're generating heat that then was leaving the system, that also had to be generating gas to do work. We'd need both of those two components. We have to have a positive delta V for the system, and we have to lose heat for the system too. All right, let's go 5 more seconds. And all right, time. I love the brave warriors that chose E as an answer. So let's do this by elimination. If a system is an isothermal, right, and it is undergoing expansion, and it is an ideal gas. So these are giving us our bits and pieces of this. So first of all, why would maybe delta E or what do we know about delta E for an isothermal system that is undergoing, that's an ideal gas? It has to be 0, right? If we say we're dealing with an ideal gas, temperature is constant, its internal energy, the absolute value of energy, is equal to or done by the temperature. If temperature is not changing, the energy must not change. A and D can be eliminated because we know that those two values are not possible if it is an ideal gas and we are not changing its temperature. That's the first. Okay, B and C. The system, it's an isothermal expansion of an ideal gas. What does expansion mean? What's the sign of work for an expansion? Yeah, it is expanding, so that means that delta V has to be positive. That expansion means that work has to leave the system. Work must be negative. If it is if the delta U or delta E is 0, and we know it's an expansion, that means that energy is leaving as work. That means it has to be coming in as heat. Yes, for isothermal systems, delta E, not U is 0, delta U is 0. That's right. And the system still has energy, but the change in energy in that system is going to equal 0 as long as the temperature does not change during that process. That's right. Okay, so yeah, the heat has to balance against that one. We know that the work value is going to be negative because it's an expansion, so it's in the wording of it all. So those are the key pieces to pick out of this. If delta T is 0, delta E for an ideal gas is also 0, we can eliminate A and D. The system is increasing in volume, which means it is doing work. Work must be negative. The last one that goes into this is we know that we have a delta E equals 0. The change in energy is 0. That means that the expansion has to be balanced, counterbalanced by the heat that's involved in the system. Last one. If heat is added to a system, is it still possible to change the temperature or have the temperature decrease? Give that one another 5 seconds. You guys are crushing that one quickly. All right, and time. So yeah, the point being, absolutely, definitely true, probably true. I have mad respect for the people that totally committed and went with A, but both of those two are positive. So really what we're trying to say here is, just because heat enters the system, you may not get a change in temperature. Just because heat is lost from a system, you may not get a change in temperature. Temperature is the sort of, it's the after effect of extra heat ending in the system or extra energy being binned in the system as seen by kinetic energy of the particles. They're not synonymous. Just because heat goes in or out does not mean temperature has to change, right? So we're trying to make sure, we talked about this a couple times, they are decoupled. They're related. It's a way of sort of getting access to heat, but it's not the only way. If work is involved, heat may not lead to temperature changes, and that can be the case of this sort of thing too. There's a lot of examples of this, and it's something we're going to start talking through, especially now we should start talking into one of my favorite topics, which is calorimetry. So one of the things that I use in the lab quite heavily is what's called reaction calorimetry. It measures the changes in heat in a system. Now the important thing, so who has heard of something like how many calories in food, or or a calorimeter in general? Is that something that you guys have sort of bumped into a bit? Yeah, like it's relatively common, right? A calorimeter is actually something that's part of our normal language about energy content of certain things. Does anybody have any idea what the name of this thing is, this apparatus? A work measuratron, right? This is barometer would be one part. It's kind of related to that. It's a pressure type meter, but really this is what we're coupling here. And this is just one. This is an example of a way to measure changes in volume in a very precise way. You can have gas barometers, you can have gas burettes that kind of do this. But in the end, as long as there's an external pressure which is constant, I could measure a change in volume, which tells me about how much work is happening here. EXT stands for external. So what we're doing here is if I had a reaction, in this case, this is adding a chunk of zinc metal into HCl, that actually produces H2 gas, which means there's a change in the volume of the system. The atoms that used to be in the solution as H plus are actually going to turn into gas molecules, which allows me to measure a change in volume. This is very, very, very tricky because we have to have a perfect external pressure. We need to know what the temperature of the system is. There has to be no friction that's involved in it. So this is not typically what people do. Because energy is balanced, we've got both heat and work as two sides of things we can use. Typically what we will do is focus on the heat. And the reason why is kind of goes back to what we just talked about things like refrigeration units. So we talked about refrigerators, taking a gas and compressing it or expanding it. That's a very common way of heating, cooling things. Has anybody seen, there's like cups, there's like a plate where you can actually plug this thing in, put your cup on it, and the cup gets cold. Has anybody ever seen something like that where you've got a device, there's nothing on it besides electricity, and the thing actually gets cold just by putting electricity on it. It's called a Peltier device. It's a semiconductor where as long as you put current across something, it can move heat. Or the opposite's true. If I put heat into these kinds of materials, I get out electricity. It's a very specific kind of device that's used in some cases. In some of its active cooling and things like some computers, where electricity can be used to drive heat as like almost like a little heat pump. It's a Peltier cooler. There's actually, if you go on like Amazon, do not do this now, please, we're in class, but if you go on Amazon and look for like a USB drink cooler, usually it's this little Peltier type of device. So, but the point is, we've got these materials that allow us to measure very carefully movement in heat, or even better, changes in temperature between reference objects. Which means we can measure based on these quantities. Heat is an easier quantity for us to measure, and it's a lot more universal. It's a lot more easy to standardize. So as a result of that, we focus on these heat measurements, which then get us access to this delta E. Now, okay, how does this thing go together? Well, there's still this problem, right? Like if we said, I am going to measure just the heat component, which maybe comes from a temperature quantity or something else, right? Heat is one part of our overall delta E. Remember the first law, heat and work are our two energy unit conversions. So one way we can measure heat is by structuring the system so that the volume does not change. If the volume doesn't change, what has to happen to work? If I build the system so that there's no possible way volume can change, if delta V equals 0, work has to be 0. So, if I have an object or reaction, and I did the reaction where the volume, wherever that reaction happens, I restrict it so that the volume can't change. So what I'm doing is deciding to set up the experiment such that if volume can't change, work must be equal to 0. So this is going on a common theme. We just talked about pistons, where to make our lives easier, we're going to hold delta T 0, which means delta E is 0, and now heat and work are nicely balanced. Now we're going to measure heat only, but we're going to do it under the conditions such that volume does not change. It is volume. It's not isobaric, that's pressure. Choric, thank you. Isovolumic, it's isochoric, thank you. It means delta V equals 0. If delta V is 0, just like before, having one value in this equation equal to 0, it kills something else. In this case, we kill the work term. What's nice about that is, in that case, doing a reaction such that volume is 0, all of the heat we measure is equal to the delta E. And we call that heat, specifically this QV term. It is the heat measured under constant volume conditions. So we can have the same reaction, but by doing it in such an apparatus that the volume is held constant, we are measuring this QV value, and by definition, QV equals the delta E. It is the change in energy such that this change happened under a very specific path. Just like the delta T case, by choosing certain restrictions, we're talking about a single path between two states. It's still a reaction where we're starting and ending in some part, but we're restricting it such that the only way to get between those two is only by using heat. We're holding the volume constant. So this is done by using what's called a bomb calorimeter. Has anybody had luck to actually play in a lab where they got to work with a bomb calorimeter before? Possibly. It's a little bit more esoteric now. In the name, bomb, right? This is one of the things that kind of comes with the value. But what we call it a bomb calorimeter is we have a reaction center, a chamber, where it is made of a pressurized vessel that never changes in volume. However much volume is in that system, the system is everything inside this reaction chamber here. That is our defined system. We place something inside the system. We usually will do the reaction in this environment. And what we're measuring is the change in temperature in a water bath outside the system. So reaction happens inside this pressurized bomb. Heat is generated. Reaction is either taking up heat or expending heat inside that bomb. The heat then moves to the surroundings. The surroundings in this case are the water jacket sitting outside that system. And the reason we use that is It's very easy to maintain how much water do we have. It's also really easy to measure the temperature it's in that water too. By changes in temperature in the surroundings, we can infer or figure out how much heat came from the system or went into the system, the plus or minus Q value here. So how this looks again, this is our point. Remember, what we're going to say is the system are these hardened steel walls. We have the surroundings, that's our water. We're measuring the temperature in the surroundings. It allows us to isolate inside here. Now, I don't mean isolated systems. We basically put everything we want to study inside this case. So this is typically used for things like food, energy content for things. So let's say this is a Snickers bar. We put the Snickers bar inside, we pressurize that system with a lot of heat, we add a spark, it burns. As that combustion reaction happens, we're converting the sugar, the delicious nougat, all the parts of the sugar, or the Snickers bar are being converted into carbon dioxide, ash, right? All the other sort of organic products of this. And as that happens, there's going to be heat as a result of that combustion that is exiting the system into the surroundings. So what's my sign? What is the sign of Q for this combustion reaction based on the way I described it? We burn something inside, heat leaves the system, right? So the Q for the system is negative. What is the Q for the surroundings? What's the magnitude? What's the relationship between those magnitudes? Q in the system to Q in the surroundings, they are equal, different signs. The system loses it, the surroundings gains it. What about temperature of the surroundings, up or down? Yeah, the water will increase in temperature. So what we're doing is we're sitting here and we're watching what happens to the temperature in the surroundings. By knowing how much water there is, what temperature we started at, and what temperature we end at, we can calculate how much heat did the surroundings either pick up or lose. Why does flavored water have calories measured, but the heat released from the flavor... Wait, what? Let me show you sort of an example of where we use this. Remember, calories like this value is just a measured internal quantity of energy estimated by a setup just like this. We actually measure if we were to combust this and move them between the two. So again, let's talk about just state functions for a second. Why does, basically, this does not look like what happens when I eat a Snickers, I hope not. This is not what happens when I eat a Snickers bar, right? If I take Snickers bar, burn it into ash, and measure the heat, why does that value have anything to do with me? Anyone to hedge a bet? Yeah, what we're assuming here, the big assumption is they are state functions. If I take a candy bar plus oxygen and I burn it, that's one possible path. I'm burning it under a constant volume system. I'm measuring how much heat goes from sugar, candy, into decomposed, fully oxidized candy. If you guys remember back biochem, TCA cycle, glycolysis, things like that. By eating sugar, our bodies are functionally big catalytic reactors that convert sugar plus oxygen into energy plus CO2, right? Like we are basically doing, it's not bang on the same. The difference between these two processes is how much energy over time. It is rate. But the overall energy content is similar. It's not perfect, right? If all of the energy, if in you, after you're done digesting it, it was identical to what's left over in there, then that energy is a one-to-one value. It's also a good ranking system for how much has more or less energy. But what we're really saying here is that they are state functions. Going from sugar to oxidized sugar is a state. And what we're measuring in this case is if we did that under this nice delta V equals 0 system, I can measure the heat. That heat is the delta E for that process. I've got a value that I could take to the bank. Now again, if I do that, it doesn't mean that's how much heat I'm going to give off. What's different about me if I eat a sugar, like a candy bar versus here? Well, all the heat, all the energy here, well, yeah, you store some of it. What else is different about when I react that candy down? Yeah, hopefully don't explode. What else? Am I a constant volume machine? Is the delta V for me as the system this? No, right? What happens to some of my volume? Right? I'm breathing out the CO2. As I oxidize that energy, I'm breathing out the CO2. So some of the energy that is contained in the Snickers bar does not end up as heat in my case. Some of it goes out as work to breathing out. So this is back to everybody else saying, oh, you need to exercise, you need to work out. No, just breathe. Delta V. We're all good. Yes, weight loss hack, exactly. Take that to Instagram. All right. So how we complete this? What we need to do here is we need some fundamental capacity questions. This is how we measure or convert delta T's into heat. And the first one is, it is called by what's called the heat capacity. A change in temperature in any object will be different depending on what that object is. This is this value C. The value C, what we call here the heat capacity of that object, it is how much energy can that object pick up before its temperature changes by 1 degree Kelvin or by 1 degree Celsius. Now, big things, stop and pause. Why does the unit of delta T not matter between Kelvin or Celsius? It does not. We're saying the unit of change, it's how much energy to change this thing from 1 degree Kelvin or 1 degree Celsius. Yeah, 1 degree Kelvin equals 1 degree Celsius. There's no magnitude or multiplicative value. It is an additive sum, right? We just put a baseline add 273.15 on it. The delta, the change in heat, the change in temperature in the Celsius scale or the Kelvin scale is identical. It is 1 degree, right? So do not get caught on this and go, oh, it went from 25 to 15. That's 5 degrees Celsius, but they're not going to catch me. I'm going to add 273 to that delta T and then I'll put it in here. No. Remember, it is the value difference between two reference values in some scale. It can be a delta C or Celsius or Kelvin. So the heat capacity value is just that. It is a measure for, think of it as an object. It is just how much heat for that thing. That could be a calorimeter. It could be my phone. It is an object. The molar heat capacity is a little different. It now normalizes the heat capacity we just measured by a certain number of moles of that object. So, saying this out, if I had a glass of water, I can measure for this water. I have no idea how much there is, but for this water, I could measure how much heat is necessary to change it by 1 degree. That is the heat capacity. If I want to know the molar heat capacity of water, I take this C value and I divide it by how many moles of water are here. That's why the molar heat capacity value has this extra thing, Cn. That now is normalized by 1 mole of that object. That means that for this, if I had the molar heat capacity value of water, I would need to know how much water is here in order to finish my value for how much heat is involved. So difference between heat capacity is it is just for an object. It is how much heat to change by 1 degree T. Molar heat capacity is for some object, 1 mole of that object. How much heat do you need to change its value? The specific heat is based on mass. 1 gram of that object has a specific heat. So these are the values that sort of convert between these two. So based on extensive variables or intensive variables, these are state variables for sure. Which of these three is an extensive variable? Will change based on the size of that system that I'm talking about. C, Cn, or Cm? Yeah, C is extensive. It's talking about the heat change for an object. We're not specifying how big that object is. Cn, Cm, it is the heat it's the energy per degree Celsius for 1 mole or for 1 mass. Those are intensive variables. They're normalized by a weight of those objects or a mole of those objects. So molar heat capacity, specific heat capacity, those are standard intensive state variables which can be used as a point. Does anybody know a C value that you should absolutely have baked into your head. Something that is a reference value. 4.184, yeah, what is that? For water, 4.184, give me units. What is that? Joules, Kelvin, we're missing something else. Grams, isn't it? Milliliter? Kilogram? I think it's kilogram. Per liter, yeah, exactly. Right. It's a certain volume. Water is our reference standard for these sort of things, 4.184. Do you remember what 1 is? What value for water, its C, has a value of 1? It's in the calories scale. So 4.184 is joules. If we're using joules as our energetic quantity, yes, that's the one you guys are probably used to seeing. That's the specific heat capacity for water is 1 gram of water will need 4.184 joules per gram to raise it 1 degree Celsius. That's right. If you're talking about specific heat in terms of calories, calorie values, it's actually a single. So that's where we can actually go through and do this calculation. If you had a Snickers bar, and you burned that Snickers bar in a bomb calorimeter. So what are we specifying? If I say I'm doing a reaction in a bomb calorimeter, what is 0 here? Delta E, delta P, delta U, delta G. Yeah, delta V is 0. That's the first thing you pull out of this point. All right, Snickers bar is burned. If 10 liters of water increases in temperature by 28 degrees Celsius, how much energy was associated with that Snickers bar? So we're going to finish off this calculation. This is the last one we're going to do today. All right. So I'm going to start off by saying the C, specific heat. For water, in terms of calories, it's equal to 1 calorie per degree Celsius per gram. That's a value that we have that, and that's partly one of the reasons for the definition of a calorie looking the way that it is. Oh, I'm going to use calories. You could use absolute kilocalories or something like this. I'm going to use calories for just a second as we walk through this value. Just again, because that's also, since we're talking about food, food is typically measured in these kind of calorie values. All right, that's our C. Now remember, the equation we're looking for is heat, Q equals MC, specific heat, delta T. Okay. What are our other values that we have here? Delta T is what? From this equation. Yeah, 28. And it is not 28 degrees Celsius. And I'm going to convert that to Kelvin by going plus. Remember, we said this. It is not starting to convert it in this way. It is just 28 degrees. It's the difference in energy between these two. All right, we've got those two. What's the last thing we need? What if this was a 5-gram Snickers bar? And we have 10 liters of water. What is the mass that I need to complete this calculation? Yes, the mass of the water. Why does the mass of the Snickers bar not enter this equation? Like, that's important, right? That tells us a total part of it. But yeah, you didn't measure that. Remember, when we're talking about this, if this is my equation, I'm saying how much heat came from some amount of mass that has a specific heat that changed by this. This delta T here is for water. You changed water by 28 degrees. How much water do you? What's the M? 10 liters, right? Now we need to convert this. We have 10 liters of water. 10 liters of water is equal to 1,000 or 10,000 milliliters, which is equal to 10,000 grams, right? So finishing this off, the total Q here is equal to 10,000 grams multiplied by 1 calorie per degree Celsius, gram multiplied by 28 degrees Celsius equals 280,000 calories, or You can also call that kilocalories, right? We could multiply it by 1,000. Does anybody know this? If I called it 280 big C calories, does everybody recognize what a big C written as calories? Yeah, this 280 calories is exactly the same thing as 280 kcal with a little c. This is why we like sticking with SI units, but just for reference in you guys too. Big C calorie is the same thing as a kilocalorie little c. So again, yeah, back in the chat. Why does this not? Why don't we care about the weight of the Snickers bar? Because the value we measure, the delta T here, is specific to the thing that was changing temperature. That's the water. So we don't need to go through this process to measure this part back out. Why don't we need to know the specific heat of the Snickers bar? Snickers bar just burned up, right? That's the thing that removed here. We're assuming under this concept that in the value, in this system, everything inside that bomb calorimeter is converted into heat. It's being done under a delta V equals 0. None of the energy is lost as work. All of it gets converted to heat under this concept. Yeah, Sam.
So are you saying that the specific heat capacity, 1 calories per change in Celsius per gram, is the same as the specific heat capacity of water?
That is the specific heat capacity of water. Yes, 1 calorie per degree Celsius per gram, little c calorie, is a standard definition of water. That's the specific heat of water. You could do the same calculation knowing 4.184 joules per degree Celsius gram. Your energy would just come out in joules value. If you look here, this is at least an older, more retro Snickers bar. Its energy here for this 2.8 ounce or 57 gram bar is 280 calories. That's where this value comes back in. So yeah, if you were to burn a larger bar, your value here, the amount of heat you would see, would be different. Changing the size of the reaction with more bar would definitely change how much heat is involved, but it doesn't mean, again, that's not the mass value that I'm sort of pointing out right here. The mass associated with this delta T, that's the biggest thing for these calorimetry questions you have to focus on. Okay, that's where we're going to end for today. This is the first introduction of a way at getting at heat directly using these values, our MC delta T, NC delta T, or just C delta T, these three different values that we're sort of going to work through. So starting through next week, on Wednesday, we'll continue on this process for other ones. All right, guys, I'll hang out for a bit for questions. Remember also, I have office hours today at 3:30. So talk to you guys soon.